Hi all. In this presentation, I'm going to discuss our new concept and results for explaining in a unified and joint framework the Hubble tension and the detections of anomalously cold spots in the cosmic microwave background temperature maps. I'm listing here my collaborators for our simulation approaches, and also giving some credit to the DES team for the observational ISW result papers that I led in a couple of years as part of DES. So, what is ISW and what is the problem with it? The integrated Sachs-Wolfe effect is a direct consequence of some kind of dark energy component in general, as in the presence of dark energy, the large-scale gravitational potentials are going to decay, and therefore, in alignment with big structures in the cosmic web at hundreds of megaparsecs of scales as supervoids or superclusters, we expect secondary CMB anisotropies, cold spots, and hotspots. In ΛCDM, this is a very weak signal, and therefore it was a surprise when in 2008 Granite et al. Claimed the 4.4 sigma detection of this signal, which then turned out to be a factor of about 4 or 5 higher than expected in the ΛCDM model. And it's still unexplained basically, but then the argument was that in ΛCDM, the signal just cannot be this big, given other precise constraints. And also, it's not really plausible with the alternative cosmologies that people typically consider. Therefore, the reasoning was that probably this is a fluctuation and it will go away. And one should, if this is a look elsewhere effect, one should just look elsewhere. And this is what we did in the last couple of years with data coming in from the dark energy survey using the year 1 and then the year 3 data set. And we did confirm that there is, again, some tension with a factor of 4 to 5 higher amplitude for these kinds of ISW template imprints that we constructed for supervoids that are observable in the DES survey. We also extended and explored the situation using some reanalysis of the BOSS DR12, CMAS, and LOSI datasets, and in some papers we concluded that this seems to be a real trouble. So there is some tension and problem with the ISW from supervoids, from the observational side. So in a more recent analysis that is the topic of this presentation, I'm going to argue that perhaps dark energy is to blame, and in some alternative cosmological models without dark energy, introducing so-called emerging curvature, apparently both the Hubble tension, which is a 4 to 5 sigma tension, and the ISW puzzle, which is a 3 to 4 sigma tensions from SDSS and DS here 3, can both be resolved to some extent. So let's see how this goes. So Avera is the name of the framework that my collaborators created, which is a simulation approach, and Avera stands for average expansion rate approximation. And the key idea is the following. So normally in n-body simulations, the evolution of the scale factor and the simulation box is governed just by the average density of the simulation that doesn't really change. There is one Friedman equation to solve with the given components of the universe that you want to model, and then the scale factor evolution comes out. As opposed to this traditional approach, the twist in this, I would say, heuristic implementation of some back reaction models, which we believe Avera is, or at least it's some simplistic model of some probably some deeper truth that can be an alternative to current paradigms. So in Avera, the basic concept is that the density in cells that we define inside the simulations can, of course, vary. It's not just cosmic variance terms, as in homogeneous and isotropic models. And in turn, since we expect that in mini universes, let's say, if the little cell's omega m parameter is relatively high, then its expansion rate compared to some cosmic mean is lower. And if in void regions where there is less matter and omega m values are smaller than some cosmic mean, the corresponding expansion rate can be higher. And then the question is how these regions, how these elements of the cosmic web are represented in the effective evolution of the simulation box and of the simulated universe. And it turns out that basically at high redshift, where this dark energy free Einstein de Sitter like Avera model is set at around redshift 9, and a similarly set lambda Planck like ΛCDM simulation is running parallel, it turns out that without the lambda term in the Avera model, the structure growth is even stronger at redshift centered around 3, and therefore the expansion rate is lower when the structure formation is more efficient. And then at late times and low redshifts, where another effect comes to dominate, when cosmic voids are beginning to dominate the volume of the universe at these redshifts, what happens is the following. So in the cosmic average, the weight of these faster growing regions becomes more pronounced because they can increase their volumes more efficiently, and therefore they end up dominating the volume averaging that is part of the Avera framework, and therefore a slower expansion is followed by an even faster expansion compared to ΛCDM. As you can see in the right panel here, the differences are not big compared to ΛCDM, but there are small characteristic differences that can be used to discriminate between the two models. This was one of the key statements of one of the first papers in this series by Kovács and collaborators. So in particular, in the case of the Hubble tension, Avera predicts or shows that the Hubble parameter h of z compared to its ΛCDM equivalent is something like 10% higher consistently at low redshifts in this framework, and this can provide some solution to the Hubble tension. And let me mention that in principle, the one free parameter in this approach is the number of cells or the cell size, and with reasonable cell sizes of about 1 megaparsec or few megaparsecs, these are the solutions that we end up with. More interestingly and more relevantly to our case, the growth rate of structure is also different in the Avera model than on the CDM, and as you can see, the difference between the different Avera model versions is smaller actually, so it's a more robust probe. So since ISW is sensitive to the growth rate of structure, we can use it to probe Vera in a completely new way. And practically, what we did was to use the Millennium XXL simulation, and in particular light cone going out to Redshift 2.2 by Smith et al. To find voids in the simulated cosmic web with the appropriate pruning of the tracer catalogs to have LRG-like halos, and then one can identify supervoids and stack. And another new idea was that actually our analysis in terms of creating the ISW maps as ray traced ISW maps for the lambda CDM and for the Avera model from Millennium XXL is not a new result in itself, because my collaborators, led by Robert Beck et al., already constructed ISW maps for the Millennium XXL mock, but in that approach, the starting point was placed to random location in the simulation, whereas in this new approach, there is now a one-to-one correspondence between the cosmic web and the ray-traced ISW maps. Therefore, we can expect to see the cold spots in the maps. So, following our previous approaches from DES, also from a bunch of other data products like simulations like Jubilee, we again did the same stacking approach using these supervoids. As you can see, these are really big structures reaching radii 100 to 200-ish. But on the other hand, they are really shallow structures with a mean under densities just like 10 to 15%. But this is exactly what we are looking for to detect ISW signals with high probability. So this is a really simple measurement, I would say, because we have the lambda CDM and the Avera ISW maps. We have the positions and sizes of supervoids in the mock, and then we just do the stacking measurement and end up with a different amplitude for these signals, as more or less expected from the fact that the Avera ISW map in general contains somehow more structure in most of the scales, more power. Okay. So in comparison to observations, which is the relevant thing in our approach, given the different growth rate of structure and different age of Z evolution, as I said, we end up with different profiles for lambda CDM and for Avera in this imprint of supervoids in the simulation. And as you can see, the agreement with the observations, which is the points with the arrow bars, is remarkably good, because previously the argument was that if this is a real signal, then it should show up in multiple data sets. This is what we have basically, and in lambda CDM you cannot explain this because it's already constrained. So this is what we see, and also when we compare our MXXL lambda CDM results to our previous Jubilee simulation-based approach, we see good agreement, which shows us that at least at the lambda CDM simulation level, we are also well calibrated. So this, I would say, is an important finding already, because this is an anomaly of lambda CDM, and Avera seems to provide some clues how to explain it, but there is actually more. And just to briefly mention another important point, that we tried also to understand why, even given the same data set, some approaches show this excess signal and cold spots, which are colder than expected, while some other approaches don't. And using the void finder by Nadatur and collaborators called Revolver, based on the very popular Zobov approach, we checked many parts of the analysis, such as what's the role of the void definition, what's the best way to prune the catalogs or to group the voids as it's provided by their so-called lambda parameter. And Long story short, it's found then in our analysis that the most relevant difference one can make in this analysis is the rescaling or not rescaling to the void angular size on the sky. And in a ΛCDM versus Avera comparison, you can see that restricting our analysis to the Bose CMS Redshift range used by these other analyses, we can see that if rescaling is done, then the separation between the ΛCDM and Avera signals is rather nice and clear, and the best fit amplitude given by Nadaturu and Crittenden's analysis is in between the two, but it's closer to the ΛCDM version. On the other hand, if you look at the right panel, without the rescaling, which is the actual approach followed by Nadaturu and Crittenden, the separation between Avera and ΛCDM signals is less pronounced. And as I understand it now, it is because in the Avera model, it's not just the high amplitude for the cold spot, but also there is stronger hot ring around these structures, such as you can see here. And if you, instead of rescaling, you mix up some different parts of the voids in terms of angular size compared to the void radius, then you can have some funny cancellation effect in the profile, and you end up with an overall signal from different bins of this lambda parameter that, due to the cancellation, becomes more consistent with ΛCDM, which needs a bit more work and thinking, but this is also a promising result in this long story of the anomaly. And the third thing that we investigated as a bonus is the Avera Model and the CMB Cold Spot. There is firm evidence for a low redshift supervoid aligned with the cold spot from galaxy density field, cosmic flows with information of subvoid, etc. But theoretically, the situation is the same as in the case of the supervoids, because you cannot claim a causal relation between the big voids and the cold spots, because in the ΛCDM model, the predicted signal is 4 to 5 times smaller than that observed in the CMB as the cold spot. So there is some theoretical arguments against this kind of causal relation. But interestingly, what we again found from the Avera framework is when looking for the coldest spot in Avera with the same spherical Mexican hat wavelet filtering as it was used for originally for the detection of the CMB cold spot, and then choosing the coldest region as the one with the strongest response to this filtering, we see really good agreement, as you can see, between the cold spot profile, again with the data points and error bars, and the Avera model. And ΛCDM is again very inconsistent with these measurements. So I would say we, in all three cases that we wanted to investigate, starting with the ISW signal, the excess signal of the supervoids, in trying to answer why in some cases there is a signal and why in others there's no signal, and how and why the cold spot might be related to the problem. We presented some successful or at least promising results. And of course, it's important to note that the price to pay was really heavy, because we introduced this emerging curvature framework and abandoned lambda and a homogeneous and isotopic model for the universe. But I would argue that this is not really a fantasy anymore, because of the confirmation of the previous SDSS and Bose excess signals from DSCO3 data, and also with our systematic analysis of all the possible factors that might influence these structures. I think we plausibly showed that this case is related to the Hubble tension. And what remains for us is to understand better other cosmological observables such as BAO, we need this emerging curvature, also the growth rate of structure. And for the future, what we want to do is to study the smoking gun signal of Avera at high redshift, that is an opposite sign ISW signal. And I think I will stop here, and thank you for listening.